Okay, we will see the solution of 2.7 part D. This circuit is given in which V in is variable. We need to go for V out versus V in, and one is given, but this is PMOS. 1 volt is connected to the gate. The drain side is connected to R1, and R1 the other terminal is grounded, and V out is connected here. So at the first glance, you will able to see that okay, can we just go for the source follower kind of thing? But as this is PMOS, something has to be connected at source to make PMOS or maybe NMOS or whatever MOS to be work as source follower, right? In previous cases, in the B and C part, our circuit was like this. That was NMOS. Some R was there, and here it was the V out terminal, isn't it? So this is source follower, but this is not. So kind of source, degenerative kind of thing, degeneration kind of thing here, and this is kind of RD. This is common source kind of configuration. Please be careful with that. Okay. So what is VGS here? The mode of 1 minus V in. So as I told previously in the video of 2.5 part D, whenever you come to work for PMOS, just be careful. You just you can go from the source point to gate point, this to that, like we are always writing VGS, but don't mind. If you want to calculate, you can write V in minus 1, or else you can just take mode of it. It will be very easier for you. Same goes for VDS, V out minus V in, but it is also in mode. Okay, so first of all, to get some I, the VGS should be higher than VTH. What is that condition? Basically this V in and this is VGS should be higher than 1 VTH from this port. So it's 1.8. If V in is higher than 1.8, this MOSFET will be on, right? This is the same case as here. Let's say this is connected to ground for, oh no, wait, let's say this is connected to 1 volt and this is variable point. Then you need to come down such that this can be more than VTH. Then and then, if I am talking about NMOS here, then and then this device will be on. Okay, fairly easy. Okay, now so that's the 1 point, that's the 1.8, right? So from here to, from 0 to 1.8, it is 0. Okay, so consider this part only as of now, right? Then VDS should be greater than VGS minus VTH. That is the condition for saturation. If you will put the values, ultimately you will get that if V out is less than 1.8, that is 1 plus 0.8, okay, then device will be in saturation, otherwise it will be in triode region. So we get the point with respect to V out, but we need to find what is the V in point here. This point we need to find. So to do so, what we can do, we can just get the current equation with triode current equation. K by 2, K is mu P COX W by L by 2 into VGS minus VTH into VDS minus VDS square. So ultimately K by 2 VDS square. VDS, instead of VDS square, you can put VGS minus VTH, because at that point particularly when our device is changing the state, I mean the region, what is condition? VGS minus VTH is equal to VDS. Okay, so you can convert it and you can find V in. After V in, from that it will be 2 into 1.8, that is this, upon kr plus 1.8. so this is the point, right? If you can see, this is 1.8 plus 2 into 1.8 upon k into r. K is mu p cox w by l. So from this point to this point it is saturation region, and after that it will follow the triode region. Equation you can find I set, this is I set, and this era, this is I triode. Okay, all right, we will see 2.8 after this video.